Good morning, everyone. What I'm going to present here is detailed microstructural and petrochronological studies on Titanite coming from Mainoites related to an extensional shear zone. And the main aim of this work consisted in test the reliability of Titanite in record the shear zone activity. But why focus on Titanite? Because in the last decades, Titanite became very important in petrochronological and microstructural studies because it's a very common accessory phase in magmatic and metamorphic rocks from middle hour crust. It is a very reactive mineral that participates in reaction with major mineral phases. Its crystal structure is very important because it managed to incorporate a huge amount of uranium and lead. And in this way, Titanite managed to record melt deformation and metamorphic events. What is important is that actually, since it's a reactive mineral, it has a huge propensity to recrystallize during these processes. And so it's important to correlate uranium lead data with chemical and microstructural features in order to better screen the evolution of the rocks. Sorry. Okay. For our aim, I focus on Titanite-bearing rocks coming from the Anzola Valley. So we are in the Ivrea-Verbano zone in the Southern Alpine domains. Ivrea-Verbano zone is studied a lot because it's representative of a fossil exhumed passive margin section of mid and lower continental crust that managed to escape the alpine subduction. And in this way, it records very nicely the pre-alpine history, and during this pre-alpine history, it experienced different exhumation rifting stages that allow the development of different shear zones at different crustal levels, and it preserved also very well the thermal evidence for lithospheric thinning. So I focus on the Anzola shear zone because it is interpreted like one of the major tectonic structures that developed during the late Triassic-Jurassic rifting. But even if it's interpreted in this way, the timing of this fault system is still poor in constrain. And so for this reason, in order to try to determine the shear zone activity, I adopt a multidisciplinary approach, starting from a detailed sampling strategy, considering also the grain scale variation. I combine classical petrographic characterization with microstructural characterization using SEM, EBST techniques, and then I applied petrochronological analysis using the laser split stream in order to get not only the isotope ratio, but also the trace element concentration. In this way, it's possible to use Titanite as an important petrochronometer, and it's possible to link chemical and microstructural and geochemical data. Starting from the study sample are Mainoites that are characterized by porphyroclastic texture with alternating layer made of clinopyrex in amphibole porphyroclast. These are surrounded by recrystallized plagioclase, and Titanite is mainly abundant in these rocks and occur in different textural positions. In one of my previous work that I published in 2022, I managed doing detailed petrological and geochemical characterization and determine the PT condition of deformation in this Mainoite that occur under upper amphibolite facies conditions. And another important thing is that I demonstrated that there is this alternating layering actually is not linked only a different mineral phases abundance, but is because we have different lithotypes that change at the thin section scale. So the amphibole rich domain actually are real amphibolites, and the clinopyrex in plagioclase rich domain actually are calsilicates. And on the basis of that, hereafter I will talk about amphibolite layer and calcilicate layer. Titanite in the amphibolite layer occur in different textural positions. It shows mainly elongated and sigmoidal shapes. and by backscatter images display lighter core to darker rim zoning. Titanite in calcificate layer occur mainly focused along clinopyrex and plagioclase layer. It mainly rounded and sigmoidal in shapes, and by backscattering images, we don't observe apparent internal zoning. Only in rare grains we have patchy zoning. For what concerns the SDM-EBSD analysis, Titanite in amphibolites is very nice and show nicely distortion increase of distortion towards rims and tips of the grains. And of the 23 grains analyzed by EBSD, only 4 resulted undeformed, and around 19 show this nice distortion. And few grains show also the development of subgrains and neoblasts. That is, in this case, this grain is like an aggregate of neoblast, and this feature is attributed to fluid rock interaction. For what concerns EBSD analysis on Titanite from calcilicates, we observe that they mostly appear undeformed. Because of 30 grains analyzed, around 20 resulted undeformed, and only 10 show nice distortion, always to focalize on the rims and tips, but actually this type of features are very rare. For what concerns uranium-lead data, uranium-lead data for Titanite on amphibolite are spread on the Terra-Weissenberg diagram, forming a cone and very nice isochron. And what is interesting to know is that we identified one population, old, intercept age at 240 million years, and a second population that is intercepted of young intercept at 189 million years. And for melanithic calcilicate, we observe a very spread of data. Here we don't identify a nice single isochron, but also here the data are spread by, are bounded by old hour intercept age at 259 million years, and young lower intercept age at 189 million years. But what was really interesting was the correlation of uranium-lead data with microstructural correlation, because Titanite from amphibolite show a very nice correlation with textural position and the uranium-lead data, because the old intercept actually coincide more with the undeformed core domains of Titanite, whereas the younger intercept, the point coincide mostly with the most deformed domains and with the domains that spread the development of subgrains and neoblasts. These features are actually observed also in calcilicate, but in a weaker way. And the same things is observed also for uranium data in chemical correlation. The Titanite in amphibolite layer show a very nice correlation between isotopic and chemical data, and the points that show higher ratio of lead-7, lead-6 are inversely correlated with rare elements, zirconium, yttrium, niobium, and uranium. And this is observed also by the rare elements pattern diagram. Whereas for Titanite in calcilicate, we observe a very weak correlation that is mostly observed for uranium-lead ratio and strontium content that is focalized at the younger intercept here. Overlapping all these features, we attributed this different signature of the two different microdomain due to two main reasons. The first one, the difference reactivity of the two different type of lithology. Second, because the two type of lithotypes have different rheological behavior related to fluid mineral interactions. And this is also testified by the main mineral phases texture that we observe in the two different lithologies, like nicely rounded big amphibole porphyroclast, and abundant syncinematic amphibole recrystallized along the matrix. Whereas in the calcilicate layer, we observe a large fracture clinopyroxene porphyroclast and nicely recrystallized tail of clinopyroxene that testify a different interaction along grain boundaries with a fluid. So Titanite show heterogeneous behavior at the microscale as a function of the composition and rheology of the microdomain and the amount of fluid circulating along grain boundaries. Thanks to the nice alignment or uranium-lead data for the myelonitic amphibolites, we managed to determine that the deformation in the Anzola shear zone ended at the Jurassic time, around 189 million years. And this time interval actually is coeval with the time interval recorded by other adjacent shear zone that outcrop in different crustal levels of the Ibra Verbano. And so we managed to say that the Anzola shear zone drove the Triassic-Jurassic rifting processes that then allowed the evolution of the Adriatic microplate. What the old age mean? The older intercept that coincide with the non-deformed domains core of Titanite is still enigmatic because actually can be attributed to two different processes, coupled dissolution precipitation processes or uranium-lead resetting. But actually, we didn't have observation and evidence of the CDP process. So we think that probably it was uranium-lead resetting that allowed the interaction and to record this age. And this probably was related to the regional heating during the stenospheric upwelling or interaction with the intrusion of mercury magma, like is testified in other works. But this still need other investigation. So in conclusion, we can say that Titanite show different textural and compositional features as a function of the microdomain composition. We managed to provide a realistic age of shear zone thanks to the combination of this correlation of and the microstructural analysis. And then it was thanks to the Titanite in the amphibolite layer that we managed to record the shear zone activity, and this is possible only if crystal plastic deformation prevail on the fluid mineral interaction. And thanks for the attention.
Any questions? Okay.
We got this discrepancy between the concept of Titanite and the light and the accessory layers. What do you think?
You mean the different signature and
the difference in the older stages you see in these different layers of the same part?
Yeah, I mean how I show here. Actually, I attributed this different signature in Titanite properly due to the different, because we have different lithologies, so different mineral assemblages that then were deformed, and then yes, there was like a strong interaction, but was focalized only at the grain boundaries. Why? Because if the process should be pervasive, actually we had to observe other things that I didn't notice. So it's for that reason that we have this variability.
Is it quick?
Yeah. Speaking about fluid interaction, have you measured chlorine in any of your Titanite?
No, actually no.
That was quick. Okay, thank you.
Thank you.